In this video, we're going to talk about 9.8 through 9.10, Power Series, and Taylor and Maclaurin series. Just going to put this all in one video since they're all kind of related topics. And this is going to be a little bit of a longer video because of the amount of content that we're going to be covering in it. So let's go ahead and get started. What you see in black would be what would be provided in the blank notes, and what you see in blue is the work that you normally would fill in. I have the completed notes here so that we can go over this a little bit faster because of how much there is to do. So let's start with the definition of a power series. Suppose A is any real number. A power series centered at x equals A is a series of the form summation from n equals 0 to infinity of c sub n times the quantity x minus a to the n, which could be expanded to be equal to c sub 0 plus c1 times the quantity x minus a to the first plus c2 times x minus a to the second, so on and so forth. So that's going to be a polynomial once we expand it, where c0, c1, and c2 are real numbers. Actually, this would be every partial sum of this would be a polynomial. Let me say that. But it's actually not going to be a polynomial when we expand it all the way to infinity. So where C0, C1, and C2 are real number constants, if the series is centered at A equals 0, the series is simplified to the summation from n equals 0 to infinity of Cn xn equals C0 plus C1 x1 here. It should be an x1. There you go. Plus C2x2 plus C3x3, so on and so forth. So suppose A equals 0 and let all the constants C0, C1, C2 equal each other, and they all are going to be equal to 1. Does the power series, the summation from n equals 0 to infinity of x of n, converge or diverge? So if we call the summation here the nth partial sum here for capital N, 1 plus x squared plus x cubed plus dot 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 plus x to the capital N, since I used a capital N there. This is the geometric series with a naught, a sub 0 equals 1. First term is 1, and the r, the common ratio that I'm multiplying by each time, is x. Recall, if the absolute value of r is less than 1, the geometric series converges by the geometric series test. So if we replace r with x here, the absolute value of x is less than 1, the series will converge. That is, the series converges on the interval from -1 is less than x is less than 1, or x is between -1 and 1 not included. But what about the endpoints? We'll need to test them. So for the left endpoint, if I stick in -1 to the series, I get the summation from n equals 1 to 0, or from 0 to infinity of -1 to the n. And that's going to alternate 1, -1, 1, -1, so on. That diverges because of its oscillating behavior. It fails the nth term test that says that the nth term has to go to 0. It's not always decreasing. All those things you could, it could fail for several reasons because of the alternating series test, or just simply by the nth term test, or just noticing this oscillating behavior here. So then we're going to test it for x equals 1, and that would be the summation from n equals 0 to infinity of x to the n is equal to the summation from n equals 0 of 1 to the n is going to be 1 plus 1 plus 1 plus 1 all the way out, and that diverges by the nth term test because the limit here goes to infinity. Therefore, our interval of convergence for the summation from n equals 0 to infinity of x to the n is -1 to 1, open interval there, or you could say x is between -1 and 1. Even though the building blocks, the terms, were polynomials in this series, the sum of the series, because of the geometric series test, is going to be equal to 1 over 1 minus x. So the sum is not a polynomial, it's a rational function. If capital N is really large, that is that it approaches infinity, the polynomial s sub n of x is exactly equal to 1 plus x squared plus dot 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 plus x to the capital N will be a really good, will do a really good job at approximating f of x equals 1 over 1 minus x, a non-polynomial function. So we saw that last time a little bit with how we could kind of trace the function in just a small interval close to the c value that we chose. Well, we're going to see certain functions here in a little bit where we actually can use these power series, especially these Taylor and Maclaurin series, to actually trace the entire function. And so this is another way to look at the idea behind polynomial approximations of functions. In fact, this is exactly what we did with Taylor series and Maclaurin series polynomials. So again, we were just tracing a little part of that curve for just a few derivatives. Now we want to try and consider when there's infinitely many derivatives and we want to trace the entire curve with one of these functions is where we're getting to. So consider the power series, the summation from n equals 0 to infinity of -1 to the n over 5 to the n times x plus 3 to the n, and find the interval of x for which the series converges. So recall that a geometric series, the summation from n equals 0 to infinity of a sub 0 r to the n converges to a sub 0 over 1 minus r if the absolute value of r is less than 1. Is this geometric? Yes. Everything is to the nth power here. So our a sub 0 is 1. If we let n be 0, we can see all these things go to 1. And our r is all this other stuff that's raised to the nth power. So there's a -1, there's an x plus 3, and there's a divided by 5 there. So since the series is in fact geometric, find the interval of x for which the series converges. So we need to take r and make it its absolute value less than 1. When we take the absolute value of it, this negative doesn't matter anymore. And the absolute value of x plus 3 in the numerator and the absolute value of 5 is 5 in the denominator. I'm going to multiply both sides by 5. And then I'm going to split up the inequality here to say that x plus 3 has to be between -5 and 5. Then I'm going to subtract 3 from every part here and say -8 is less than x is less than 2. Remember to check the endpoints at -8 and 2. So for x equals -8, I'm going to be sticking in -8 in place of x here, and I get a -5. That's where this -5 comes from here. And then -1 to the n times -5 to the n is 5 to the n, which will cancel out with that 5 to the n and give me 1. We already know that diverges. 1 plus 1 plus 1 plus 1 goes to infinity. If I stick in 2, then 2 plus 3 is 5 to the n. And this 5 to the n and this 5 to the n will cancel. And that's -1 to the n, which is 1, -1, 1, -1, and we know that diverges. Therefore, the interval of convergence for the summation from n equals 1 to infinity of -1 to the n over 5 to the n times x plus 3 to the n is the open interval from -8 to 2, or we could write that as x is between -8 and 2, not included. So what exactly does the series converge to on that interval? So we would have a function f of x is equal to 1 over 1 minus r. Remember, r was negative, so subtracting a negative there is going to be a positive. I don't like that denominator there, so I'm going to multiply by 5 over 5, and I get 5 over 5 plus x plus 3. So that's 5 over 8 plus x, or x plus 8. And it converges to this as long as we're on that interval of convergence from -8 to 2. So you can apply the same rationale that we've been using with the geometric series to other types of series as well. Just modify the appropriate test accordingly to use what the test tells you about convergence to determine the intervals of x for which the series converges. So specifically, we're going to be trying to use the ratio and root tests later, and I think we're going to use all ratio tests here in the notes. We're not going to use any root tests, but the root test is another one that you're going to be looking to a lot for convergence of power series. So I don't have the actual theorem numbers from the textbook here. They are from chapter 9. So instead of 9 point something, they're just labeled with Roman numerals here. You can go back and look them up in the textbook and use them if you want. They're going to be worded a little differently than this. But let's look at the theorem for convergence of power series, which is 9 Roman numeral 1. So suppose that the summation from n equals 0 to infinity of c sub n times x minus a to the n is a power series centered at x equal a. Then one of three things can happen. First, there can be some positive number, capital R, such that the series converges absolutely in the interval of absolute value of x minus a is less than r, and that r is called the radius of convergence. We use capital R for radius of convergence. 2, the series converges for all real x values, and that would be r equals infinity here is when that happens. And the series only converges at x equals a. We know it. We know they're identical at that point. But what if the function and the series differ everywhere other than at that point? Then we'll get a radius of convergence at 0. And so consider the Maclaurin polynomial approximating the approximation of f of x is equal to e to the x. And we talked about this one last time, I think, where we have the summation from n equals 0 to infinity of x to the n over n factorial. And if I found the nth partial sum of that this would be x to the 0 over 0 factorial plus x to the first over 1 factorial plus x to the second over 2 factorial plus dot 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 plus x to the n over n factorial, like that. So note this is a Maclaurin power series. It's centered at 0. I don't have x minus a or x minus c or anything like that. So what is the interval of convergence of this particular power series? Since this isn't a geometric series, since we have this n factorial going on here, we don't have anything, we don't have everything just raised to the nth power like we did before. We can't use the geometric series test, and we need another test to use. And we'll need to use the requirements of that test for convergence to determine for what values of x the series converges. So this would normally be just a question to ask you in class. What test should we use here? Stop and let you think for a second, but because we've got nth powers and n factorials, we're going to use the ratio test. And the ratio test is going to be our go-to test for finding the radius of convergence and the intervals of convergence. So it's never a bad idea to look at the limit first to make sure that we aren't dealing with a divergent situation, in which case the problem will be very short if that happens. But just look at this and say, okay, we've got something that x is going to be a real number that gets chosen. So we have something that's exponential up top that's base to the n over n factorial. Well, n factorial grows faster than an exponential function. So this is going to go to 0. Now, saying that it passes the nth term test and doesn't diverge doesn't necessarily mean that it does converge, but this gives us really good suspicions that there should be at least one x value here, namely 0, for which if I would put it in here, 0 plus 0 plus 0 plus 0 equals 0, and it's going to converge, right? So that's kind of trivial, but that's the way that it is for most power series, is it's going to converge at its center. Since this is centered at 0, then we're pretty sure that it will at least converge at that point, since the whole series doesn't blow up and diverge and go to infinity, right? So that's all that this is telling you here. It's not absolutely necessary that you do that first, but you're going to get some good information to tell you that you don't need to do a whole lot of the problem if you know that that's what's going on. Because if it's divergent everywhere other than at that center point, then you know that your radius of convergence is 0 and your interval of convergence is x equals your value for the center of your series. All right, our an here was xn over n factorial, and our an plus 1 is going to be x to the n plus 1 over n plus 1 factorial. We're going to find the ratio of the n plus 1th term divided by the nth term here, and take the absolute value of that and find the limit as n goes to infinity. And I've done that out for you here, that you need to divide, and when you divide, you multiply by the reciprocal here. We need to make sure that that ratio there, that the absolute value of it, the limit as n goes to infinity, is less than 1, so that it meets the criteria for convergence for the ratio test. The n factorial cancels out with the n factorial from n plus 1 factorial and leaves me with n plus 1, and the x to the n plus 1 minus n. When I divide like bases, I subtract the exponents, will leave me with x to the first, which is x. So I'm going to have the absolute value of x over here, and I have, it's okay to leave these in absolute value bars. I don't absolutely need them, but because n is a positive number and it's going to positive infinity, but 1 over n plus 1, the limit as that goes to infinity is 0. 0 times anything is 0, and the x's disappear. So the convergence here is not based on x at all. Since n took care of it here, 0 is always less than 1, and that's true for all values of x. Our interval of convergence is x is any real number, all real numbers, or the real number line here, negative infinity to infinity, if you want to express your answer in interval notation. Next example, for which values of x does the power series the summation from n equals 0 to infinity of negative 1 to the n times x plus 3 to the 2n plus 1 over 2n plus 1 converge? We're going to see 2n plus 1, 2n minus 1 a lot in the notes today. Maybe not a lot, but enough that I just want to tell you that's an odd number. 2n plus 1 or 2n minus 1 is an odd number. 2n is an even number. When you add or subtract 1 from an even number, you get an odd number. So let's note this is not geometric, because we don't just have things to the nth power here. We have these extra n's down here in the denominator. That's going to make it not be geometric, so we're going to have to use a different test. Our go-to test here is going to be the ratio test. Also, the root test works if everything is to the nth power, but that's not what we see. We especially want to use the root test when we see an n to the nth power. We're not going to see any of those in the notes today. So hopefully we get lucky with the cancellations like we did with e to the x. There's nothing lucky about it. It's designed to work that way, but get fortunate cancellations like that happen with the ratio test, and that's on purpose. That's why we're using it. So recall that if the limit as n goes to infinity, the ratio of the n plus 1th term divided by the nth term is equal to 0. That allows us to conclude that the series approximation converges for all real values of x, like it did for e to the x, and that the interval of convergence is going to be all real numbers. Just remember how we did that in this previous problem. That's one of the things that it can tell us. If we get to infinity, infinity is never less than 1, and there's no interval for convergence because it's just the answer that is centered, the value for which it's centered at. So I know that sounds backwards. You're not finding the radius of convergence over here. You're taking the limit, and if I'm dividing 1 by infinity, I get 0, and yeah, that's not gonna, the only way the absolute value is 0 is if it's 0. So all right, let's use the ratio test now for this particular example, taking the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. It's going to be the limit as n equals infinity, and I put the n plus 1th term here, and I multiply by the reciprocal of the nth term here, just because we know that that's what that division is going to do. I'm not really interested in the -1 to the n powers because it's either going to end up to be 1 or -1, and that's going to go away with the absolute values there. I do want to simplify this up here, turns into 2n plus 3, and this turns into 2n plus 3, and that stays 2n plus 1. So now I'm going to get my n parts together with this limit for n, and there's no n's over here, so I'm just going to leave that by itself. And this limit here, degree of the top and degree of the bottom are the same, so I'm going to look at the ratio of the leading coefficients. 2 over 2 is 1. So I have this that I'm ready to say, okay, that means that, switch back to blue, the absolute value of x plus 3 squared needs to be less than 1. And is that possible for that to happen? Yeah, that can happen. So what I'm going to do with that is I'm going to say that going to have x plus 3 squared is what I'm going to look at, and I'm going to subtract the 1 from both sides so I can make a difference of 2 squares here. And then I'm going to factor x plus 3 plus 1 and x plus 3 minus 1 gives me x plus 4 and x plus 2. That'll be less than 0. Put those on the number line like we did in pre-calculus and put open circles there because I don't want it to be equal to 0 here. And then I test a number in each of these intervals here to see what happens here. And this is going to be negative between -4 and -2. And that's what I want. I want less than 0 is going to be negative. So I know it converges between -4 and -2, but what does it do at -4 and -2? We need to test the endpoints. So for x is -4, I'm going to replace x with -4, and that's going to give me an odd power of -1 here. And later, I'm going to actually just replace it. Oh, I did that right here. So an odd number of -1s is going to be a -1 right here. So this is -1 to the first. And so that's going to be simplified down to -1 to the n plus 1 here. So this is an alternating series with an an of 1 over 2n plus 1. That an is related to the harmonic series. I see an n to the first in the denominator. So I'm not interested in absolute convergence here because I'm certain the an this way right here diverges. So I'm going to just jump straight to the alternating series test and take the nth term, test of that a sub n, and it does go to 0. And now I need to prove that a sub n plus 1 is less than a sub n for all n greater than or equal to some n. So I did that off to the side here, 1 over 2 times n plus 1 here over 1 over 2 n plus 1. So I'm going to cross multiply here because these are going to be positive numbers. I can treat that like it's an equal sign. And so that's going to be 2 n plus 1 is going to be less than 2 times n plus 1 plus 1. So distribute this. 2n plus 1 is less than 2n plus 2 plus 1. 2n plus 1 less than 2n plus 3. Subtract the 2 n's from both sides is 1 less than 3. Yes, always, all the time it is. And the boundaries for the summation start at 0. So this is going to be true for all n greater than or equal to 0. It's actually true for all n values, but we're just interested for this series. It's going to converge for all values of n. That's true. Therefore, it's going to be true for all values of n. I just needed it greater for n greater than or equal to some capital N, but it's good for all of them. So therefore, the series is conditionally convergent at x equals -4 by the alternating series test. Let's now look at x equals -2, and I'm going to replace the x with a -2. That's going to be -1 to the n, and that's going to be 1 to any power is 1. Doesn't matter whether it's even or odd. So that part just kind of goes away. I have the series from n equals 0 to infinity of -1 to the n over 2n plus 1. That's basically the same series as up here, even though the sign changer is a little bit different. It's also an alternating series with an an of 1 over 2n plus 1. So again, we use the alternating series test to see the work above, and the series will be conditionally convergent at x equals -2 by the alternating series test. I don't need to do the same work all over again when I just did it. Just go ahead and refer back up here and say it's the same work. So conclusion, our original series converges on closed interval -4 to -2, where you can write it as -4 is less than or equal to x is less than or equal to -2. That's the interval of convergence. The radius of convergence here is going to be this number right. I didn't use the ratio test. So it was centered at -3. Yeah, centered at -3. So this is radius of convergence is 1 here. Because going from the center, I want 1 to the right and 1 to the left. All right, next example, consider the series, the summation from n equals 0 to infinity of the quantity 2x raised to the n over n plus 1. This is, again, not going to be geometric because I've got this n plus 1 part in the denominator. If it was just the 2x to the n, it would be geometric and it would be oh so nice. So I probably want to think about what this is x minus what? Where is it centered at? I probably want to think about that for the sake of finding the radius of convergence later. Just like I did in this problem up here that I had to say where was I centered at and what was I adding or subtracting to that center there. So I'm going to need to know that I'm centered at 0 there. And let's use the ratio test right away here, since that's going to be what we're going to be using when it's not geometric, unless we're using the root test, which we're not using in any of these examples because the ratio test is what you're going to use like 99% of the time. So again, we get these fortunate cancellations, and we're left with n plus 1 over n plus 2 here for the limit as n goes to infinity, and we're left with a 2x in absolute value bars for the rest of it, and that has to be less than 1. This is going to be 2, can come out of here, times this limit is 1, so I have 2 times the absolute value of x is less than 1, so the absolute value of 1 has to be less than 1/2. When I solve for the absolute value like that of x minus c, which c was 0, so the absolute value of x here, this is my radius of convergence, capital R, and then I change that into an interval of convergence by taking the positive value on the right and the negative value on the left and solving for x. If there was some subtraction in here in x minus a or x minus c, there's not, so there's my interval of convergence, but I need to test the endpoints. So I'm going to come here and check the left endpoint at x equals -1. I'm going to have -1 to the n over n plus 1, which is going to be an alternating series. I know that that an is going to be related to the harmonic series, so I'm not going to test for absolute convergence. I'm just going to jump straight into the alternating series test. The limit of 1 over n plus 1 goes to 0, so that's good. Is it decreasing for some n greater than, or for all n greater than or equal to some capital N? I did that work over here, 1 over n plus 2 less than 1 over n plus 1. Yes, always, all the time, because n plus 1 is less than n plus 2. Then we subtract n from both sides, and 1 is less than 2, always, all the time. So it's going to be true for all n greater than or equal to 0, since the summation started at 0. So it's conditionally convergent at x equals -1/2 by the alternating series test. I'm going to come back and try the right endpoint of x equals 1/2. Stick that in there. That's going to be 1 to the n. So that's going to go away, just become a 1. That's going to be 1 over n plus 1. And that's not going to converge because that's related to the harmonic series. I'm going to use the limit comparison test to prove to you here that it doesn't converge. So I'm going to choose Bn to be 1 over n if my an is 1 over n plus 1. I'm going to take the limit as n goes to infinity of an over bn. And when I multiply by the reciprocal of the denominator, I get the limit as n goes to infinity of n over n plus 1. Degree of the top and degree of the bottom are the same, so ratio of the leading coefficients is going to be 1. So the summation of an and the summation of bn both converge or both diverge. Summation of bn diverges by the p-series test because n equals 1. So an summation an also diverges by the limit comparison test. So this series diverges at x equals 1/2. So we get a half open, half closed interval of convergence here. So the series converges on the interval -1/2 less than or equal to x less than 1/2. So it's going to be closed on the left-hand side and open on the right-hand side. So we've seen some where it's completely open, some where it's completely closed. Now we've seen one where it's half open, half closed. Summary of general tips for analyzing power series. Use the ratio test, and sometimes the root test will be helpful when there's a whole bunch of nth powers, especially an n to the nth power. to determine the interval of convergence for the absolute value of x minus a is less than r. And remember that it converges absolutely there since we are using absolute value bars in the ratio or root test. Note that if if r is equal to infinity or r is equal to 0, we're done, because we know that we either have all real numbers as answers or only the center as an answer there. When that happens, if you get a finite positive r, then we know that the series converges absolutely if we're in the interval a minus r less than x less than a plus r, but we also have to test the endpoints at x equals a plus r and x equals a minus r. The series is definitely going to diverge outside of this interval. We know it converges inside the interval. We need to test the endpoints of the interval to see what happens, convergence or divergence at the endpoints. So moving on here to talk about Taylor and Maclaurin series. We've already defined what a Taylor and Maclaurin polynomial are last time. They're approximations of functions of f of x using the n plus 1 that many derivatives of f of x. Like if we want the polynomial of degree 4 or something like that, to approximate it, we had to go out to the 5th derivative, is what that's saying. The first 5 derivatives, including the 0th derivative. I guess you could say it that way. So anyways, the definition of a Taylor series here, suppose that f of x has derivatives of all orders in some interval containing x equals a. So up, as large as you want n to go. You can go as big as you want to with the derivatives. Then the Taylor series for f of x centered at a is the summation from n equals 0 to infinity of the nth derivative at a over n factorial times x minus a to the n. No x equals a equals 0 is going to be a Maclaurin series. This is just the definition for a Taylor series. Since a Maclaurin series is going to be a special case of the Taylor series, we won't give it its own definition other than to say that this is just going to be a simple x to the n over here for a Maclaurin series, which makes our life much nicer when we can write it that way. The main one that we're not going to be able to write as a Maclaurin series is going to be ln of x, since x is not, since 0 is not in the domain of ln of x, then we're not going to be able to use it as the center. Same thing for 1 over x. We're not going to be able to do that since it's not defined at 0 either. You can't use a center value that is an asymptote or a whole. So suppose f of x has a Taylor series approximation centered at x equals a, and its radius of convergence is r, then the Taylor series provides an exact representation of f of x in the interval a minus r less than x less than a plus r. Fun fact here, if you get a radius of convergence of infinity, then your Taylor series approximation is not really an approximation, it's an exact representation of the function everywhere from negative infinity to infinity. The whole curve is going to get traced with this Taylor polynomial, this Taylor series, we're going to call it. So let's generalize the Taylor polynomial P4 that we did last time for the function f of x equals ln of x centered at 1 to obtain a Taylor series for f of x equals ln of x centered at 1. So when we saw the first 4 terms here, it was f of 1 plus f prime of 1 times x minus 1 over 1 factorial plus f double prime of 1 times x minus 1 to the second over 2 factorial plus f triple prime of 1 times x minus 3 factorial, x minus 1 to the third over 3 factorial, plus 4th derivative at 1 times x minus 1 to the 4th over 4 factorial. And let's see if we can generalize that now when we went and found the pattern for the nth derivative, which we did last time. We found it to be -1 to the n minus 1 times n minus 1 factorial over x to the n. And that was defined for n equals 1, 2, and 3. So this one's going to be a little different for our summation, because normally our summations start with n equals 0, but our summation here is going to start with n equals 1. I'll make note of that again in just a second. But we do want to go ahead and plug in our x value here that we're centered at, so that we can get rid of this x to the n part down here. And that's going to be -1 to the n minus 1 times n minus 1 factorial over 1 to the n. 1 to the n is going to be 1, leaving us with -1 to the n minus 1 factorial. -1 to the n minus 1 factorial is what my nth derivative at 1 is going to be for this function centered at 1. So 2 points here. There's an n factorial term in the denominator of the Taylor series expansion that we can't forget about. So when we write ln of x, we need to write it as the summation n equals 1 to infinity. We'll talk about why that's 1 in just a second, when the definition up here said 0. See, the definition says 0, and I'm writing 1 there. Just give me a second and I'll explain that. So this is -1 to the n minus 1 times n minus 1 factorial over n factorial here. This part I had written out with the x to the n's before, but they went away because they went to 1. So that's why this is some goofy spacing here. Just see if I can go back and rewrite that. There we go, like that. And that's the n factorial from the definition right there. And that n factorial, I can write it as n times n minus 1 factorial, and the n minus 1 factorials cancel, leaving me with the summation n equals 1 to infinity of -1 to the n minus 1 over n. Notice that n equals 0 is excluded because ln of 1 is equal to 0. So we don't need to write the n equals 0 case. If we were centered anywhere else other than 1, our first term would not be 0, and we would need to account for it. So our answer here is going to be n equals 1 to infinity, some of the summation -1 to the n minus 1 times n minus 1 factorial over n factorial is, well, we did all that cancellation already here and said that that was I forgot to write the x to the n part. X minus 1 to the n. There we go. So that's our answer right there. We already had that over there. I don't know why I wrote all of it again, because I already did all that up there, but there it is. That's from right up here, just writing it down again, n equals 1 to infinity, -1 to the n minus 1 over n. And again, this one is a little different than normal. We're starting at 1 because the zero term is 0, so we don't need to write it. All right, next example, actually same function, but just part 2 of it on what interval does the Taylor series here for f of x equals ln of x centered at x equals 1 converge. So we're going to do the ratio test on this, and we're going to get, here's the function right here. So limit as n goes to infinity of the absolute value of -1 to the n minus 1 plus 1 is n, x minus 1 to the n plus 1 over n plus 1, multiplied by the reciprocal of all this. This is going to be an n in the numerator, and -1 to the n minus 1, and an x minus 1 to the n in the denominator. So I really don't care about all these -1 to the something or others here, because they're going to all turn to 1s. So then I'm interested in writing the n over the n plus 1 part, and then x minus 1 to the n plus 1 divided by x minus 1 to the n is going to be x minus 1 to the first, and absolute value bars over here. This goes to 1, so it's not going to affect anything. The absolute value of x minus 1 is less than 1. Notice r is 1, c is 1 here. So I could just figure out 1 plus 1 is 2, 1 minus 1 is 0. And that would give me my interval of convergence, but I solved it all by saying x minus 1 is between negative of this is -1, positive of that is +1, and then adding 1 to everything. 2 different ways to get the same answer there. So don't forget to check the endpoints. At x equals 0, I'm going to have -1 to the n minus 1 over n times 0 minus 1 to the n. So that's going to be a -1 to the n, and that's going to be a -1 to the 2n minus 1, which is a -1, all over n. This is the opposite of the harmonic series, but the negative sign doesn't change convergence or divergence of the series here. It's going to diverge by the p-series test. And then at x equals 2, I'm going to stick 2 in here, and that's going to be the summation from n equals 1 to infinity, -1 to the n minus 1. 2 minus 1 is going to be 1 to the n, so that's not going to change anything, over n. Now this is going to be an alternating series. I already know that 1 over n is not going to converge, it diverges, so I'm going to jump straight into the alternating series test. We should already know that this one converges. That's the first case that we usually learn about with the alternating series test. Limit as n goes to infinity of 1 over n is 0. Is it always decreasing? 1 over n plus 1 less than 1 over n? It certainly is, because n is less than n plus 1, and then 0 is less than 1. So the series is conditionally convergent at x equals 2 by the alternating series test. So the conclusion that we come to is the Taylor series approximation of f of x is equal to ln of x converges on the interval of 0 less than x less than or equal to 2, did not converge at 0, diverged for the lower boundary, converge conditionally for the upper boundary. So we have an interval of convergence of open on the lower side and then closed on the upper side. That's the other way we can write it with interval notation. All right. Now, kind of a longer example. I think this is the last example here. Let's actually derive the Maclaurin series for f of x is equal to sine x and determine the interval of convergence. This one's kind of funky, but you'll see what it means for sine to be an odd function. The first thing we're going to do is we're going to take the derivatives out for sufficiently many to determine the pattern here. So we get f of x is sine, and then f prime of x is cosine, and then f double prime is negative sine, and then f triple prime is negative cosine. And then fourth derivative is going to get back to sine again, and we see that there's this loop that we're going in here. Every 4 is a pattern, right? So we're back to sine again, and then we're back to cosine again, and so on. So we see this pattern of every other 1 is 0, and then for the non-zero ones, every other 1 is 1, and the other one is -1, and so on. So let's just write out the first few terms here of this, that this would mean that this was going to be 1 here, x, this should be a 1x, x, 1x over 1 factorial here from that one, a minus a 1 x to the third over 3 factorial, plus a 1 x to the fifth over 5 factorial, minus, I went on to the next one, minus a 1 x to the seventh over 7 factorial, dot, dot, dot. And I see that my summation here, I should be able to write it for all the odd powers of x here. I told you earlier, an odd power will be 2n plus 1. Just check it if I'm starting at 0. I need 0 plus 1, not 0 minus 1 to get that first one right there. The sign changer goes positive, negative, positive, negative. So I want that to be -1 to the n, so that the 0 will make it positive, and then the 1 will make it negative, and so on. And I want my factorials to match these powers here, so that's 2n plus 1 factorial, and that's going to be my Maclaurin series for sine x. Now, what is the interval of convergence of the series? I went with the series again down here. We're going to use the ratio test. And this is -1 to the n plus 1, x to the 2 times n plus 1 plus 1 is going to be 2n plus 3. This is going to be 2n plus 3 factorial, times the reciprocal of this one is going to put a 2n plus 1 factorial on the top, and x to the 2n plus 1 in the bottom, and this -1 to the n, and that -1 to the n plus 1. I'm really not worried about them because of the absolute value parts. They're not important to me. And I'm going to get the n parts together, 2n plus 1 factorial in the numerator, 2n plus 3 factorial in the denominator. And then I have x to the 2n plus 3 divided by x to the 2n plus 1 is going to give me x squared left there. When I expand the factorial here to get down to 2n plus 1 factorial from 2n plus 3, I have 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And that leaves me with the limit as n goes to infinity of 1 over 2n plus 3 times 2n plus 1, which definitely goes to 0, and 0 times anything is 0, no matter what that is. So since this limit converges to 0 over here, my radius of convergence is going to be infinity, and it converges for all real numbers. Which you can say like that, or you can say -infinity to infinity. So that's it. That was a lot to go through for those 3 sections, but that basically finishes up our discussion of Chapter 9. And we'll come back next time and we'll start talking about our topics from Chapter 10, which are involving parametric and polar equations and the polar coordinate system, and how to parameterize functions, and how to deal with derivatives and integration in those systems. And that'll be a nice way to talk about some types of functions that we haven't been able to talk about yet in rectangular form. The XY coordinate system, we just haven't been able to draw certain types of things. We thought that everything had to pass the vertical line test to be a function, and that's just not going to be the case when we have functions that are in terms of the parameter t, like time, or in terms of the parameter theta for an angle. We're going to be able to get some very interesting looking functions in Chapter 10, and that'll be a nice introduction for you into some skills that you're going to need in Calculus 3. If you're going into Calculus 3, you'll be doing a lot of work in parametric and polar form in that class. So that's it for this video. I look forward to seeing you for the videos for Chapter 10 starting next time.